In this seminar on standardized automotive audio measurements, I'm first going to outline the AES TC-AA white paper, the scope, measurements, equipment, and test configuration. Next, I'll talk about practical considerations, how we get the test signal into the infotainment system, and the configuration we use to make the measurements. Then I'll discuss a range of measurements that you can make to characterize in-car audio, both measurements from the TC-AA white paper, plus others that you can make with the same equipment for more complete analysis. So what is the TC-AA? In 2020, the AES Technical Committee on Automotive Audio, known as TC-AA, formed a working group to create recommendations for making in-car acoustic measurements. Many manufacturers already measure car audio, but there's no consensus on how measurements were made, so it's hard to make repeatable measurements and compare data. The TC-AA wants to create published guidelines and standard, well-documented measurement procedures to ensure repeatable measurements. This will allow comparisons, improve interpretation of results, and make system-level specifications and requirements more meaningful. This, in turn, will facilitate alignment between vehicle manufacturers, OEMs, and Tier 1 suppliers. And that's what we've been working on for the past 2 to 3 years. I've been a member of this working group, which includes experts from car manufacturers, infotainment system providers, and test and measurement equipment suppliers. Companies like Volvo, PSA, Nissan, Bose, Harman, and of course Listen, and more. There's also an advisory subcommittee that focused specifically on the details of the measurement microphone array. In October 2023, we published a white paper with suggested methods and guidelines for measuring in-car audio. And for the past year, we've been encouraging automotive audio people to make measurements using these guidelines. The feedback we receive will help us to further develop the recommendations to be useful to everyone. Let's start by outlining what the white paper covers. At this stage, it only includes objective measurements in a stationary vehicle, and it's limited to the 3 most common measurements: frequency response, Max SPL, and impulsive distortion. The test conditions are specified. Both the test environment, the car must be stationary in a quiet environment, and the equipment and positioning. We also define the audio system settings. Lastly, the test stimuli are clearly defined. In fact, we even provide reference wave files to make it easier. There is a bit of flexibility with some of the measurements, but the guidelines state that it should be clearly documented where it differs from the suggestions. This means it should be repeatable if needed. So what equipment do we use to make measurements according to the standard? The white paper doesn't specify the measurement software. In fact, it doesn't specify that it must be a software-based system at all. But it does state that it must be able to measure calibrated overall sound levels in dB/SPL, both A-weighted, C, and Z-weighted, as described in the IEC 61672 standard, and versus frequency. It also specifies that it must be able to take the independent signals from a 6-microphone array and power average them to measure a 30-second LEQ. The LEQ is the level that, if it had been steady during the measurement period, would represent the amount of energy present in the measured fluctuating sound level. It must also be able to display results in standard 1/3 octave bands. These performance specifications really mean that software is the best option. Software-based systems are also practical. They can trigger test signals without a person in the car. They automate much of the process and display results in clear graphical format. They also offer a much greater range of capabilities and flexibility. So you can use the same system for many other kinds of automotive audio measurements. Alongside your software, you're going to need an audio interface suitable for powering and converting the microphone signal input to the computer for analysis. You may also need additional hardware depending on how you will play the test signal. For example, if the signal is played via Bluetooth, a calibrated Bluetooth interface is also necessary. And you'll need microphones to capture your test signal. The white paper is very specific about microphones and the array they must be mounted in. In fact, there was a separate subcommittee that focused on just the microphones and developed extensive guidelines. They specify a 6-microphone array with accurate measurement microphones, but there's a lot more to it than that. Let's take a look. The white paper details the exact type of microphone required. Here is the spec. As you can see, it needs to be a 1/4-inch microphone, and it's quite specific about the sensitivity, dynamic range, and frequency range. What this essentially comes down to is that you need a good quality 1/4-inch measurement microphone, something like our own SEM or similar products from B&K or Grass. What really matters is to be able to accurately measure Max SPL without overload and distortion above the background and measurement noise floor. The microphone setup is also very important. The microphone array is located where it best represents a human listener. The science behind this is fully detailed in the appendix to the white paper, so if you're interested, you can download the document and read all the details. On a practical level, the 6 microphones should be numbered and mounted in this array configuration. You can see the exact position of each microphone is specified, as well as the precise angle of the array. Let's now look at what a test configuration might look like. Your signal should be played out of all the car loudspeakers in mono, which means you need to get it into the head unit. We'll talk more about that in a minute. The signal is captured by the microphone array, and the signal is transmitted via an audio interface to the computer for analysis. This calculates the spatial or power average of the 6 microphones. The paper doesn't specify a playback method, but says it should be described in the documentation. That's actually one of the biggest logistical challenges with these measurements. Getting the test signal into the head unit to play out of the speakers is not always straightforward. 3 methods are commonly used: Bluetooth, memory stick, and via the cloud. Let's first look at Bluetooth. Here we insert a Bluetooth interface between the PC and the head unit so that the test stimuli can be transmitted. This is the method I use most, as it doesn't rely on proprietary access to the car's head unit. It also lets you control the playback via the test software, which makes it easier to do remotely. The downside is that it requires an additional piece of hardware, a Bluetooth interface. Note that it's important to use a high-quality calibrated Bluetooth interface with A2DP, one that's designed for audio testing and allows a precise control of the codec selection and test level. You can't use a cheap consumer-grade Bluetooth transmitter. The second way you can play the signal is from a memory stick. This is simple, but it needs the head unit to have a USB input, and not all cars have one. It also means someone needs to be in the car to start the test stimulus, then quickly get out before measurements begin. Some of these measurements use rather loud test stimuli. On the analysis side, it needs an open loop stimulus with record triggering so that stimulus and response waveforms can be aligned to overcome large time delays. The third method is playing the signal via the cloud. You can play the signal either via the car's internet-connected music application or a phone with Android Auto or Apple CarPlay. This requires additional setup. For example, hosting your test stimuli in the cloud with a streaming service. Calibration and measurement is more complex as you have extra variables like the phone and streaming service. And like the USB method, it needs open loop analysis with record triggering. Now let's look at where we put the microphone array in the car. The white paper gives us a couple of placement options. If you have head location data available, which is only usually an option for OEMs, you can place the center of the array at the median head location and document that point. Without head location data, the array should be positioned where an average person would sit comfortably. This is documented relative to fixed points in the car's interior, such as the steering wheel, driver's seat, and brake pedal. Measurements should generally be made in at least one seat from each row. We've actually already had some feedback that there should be more options for microphone positioning. Our friends at Ferrari presented a very interesting paper on audio measurements in sports cars at the AES Automotive Show. And they had problems with the standard array configuration fitting nicely in their sporty seats. So we may need to have some alternative options. This is the sort of feedback that we only get when people start making measurements. So we'd love to know how these configurations work for you. So that's the test setup. Now let's talk about the stimuli we are going to use. These are the 5 stimuli I use in the measurements I'm going to present. The white paper recommends correlated pink noise for the frequency response and Max SPL, and a sine sweep for the impulsive distortion. I'm going to be showing you some additional measurements that use uncorrelated noise and tone burst. Now let's look at the setup in practice and make some measurements. I don't have a test bay, so I made these measurements in a quiet underground parking garage in a modern electric SUV. I used the Bluetooth configuration that I showed you earlier. I like this method best for a couple of reasons. First, it's the easiest to set up, and it does not depend on any special access to the car's head unit. It also integrates with my test sequence for full automation, which saves a lot of time. You can see I have my 6 mic array here in the driver's seat. It's positioned following the guidelines in the AES white paper. It's at a height of 74 centimeters with a 30-degree angle, centered in the driver's seat, with the microphone stand legs positioned against the back of the driver's seat. The distance between the closest microphone and the headrest is 10 centimeters, and the brake pedal to backrest distance is 100 centimeters. Before we start, I'll make sure the front passenger seat is in the same position as the driver's seat. Here in the trunk, I have an AmpConnect 621. This audio interface supports 6 microphone inputs and has a wide dynamic range with auto ranging. This helps ensure a good signal-to-noise ratio for more accurate measurements. On the table here is my Bluetooth interface connected to the laptop. This will send the stimulus signal to the head unit. Note that it is critical to use a test-grade Bluetooth interface with an A2DP codec for the best frequency response and signal-to-noise ratio. The AmpConnect 621 is connected to my laptop running SoundCheck software. This, as you probably know, is a full-featured and flexible audio test system capable of making all the measurements outlined in the white paper. Particularly important is its ability to power average the inputs from the 6 microphones in ISO standard 1/3 octave bands that's required for most of the measurements. Before making any measurements, I calibrated both the inputs and outputs of the test system. I measured the sensitivity of each individual microphone in the array with an acoustical calibrator and stored these readings in the software calibration menu. Acoustical calibration is better than reading TEDS data from the microphone because it accounts for the actual measurement conditions, including temperature and cabling losses. I also calibrated the audio interface to ensure proper response frequencies and level, both in the analog and digital domains. Okay, let's get measuring. We'll start with the frequency response. This is the clearest indicator of overall performance. If frequency response is outside the limits, the tonal balance is affected and the audio system may not sound as intended. We're looking for a smooth and gently sloping frequency response, usually with more bass than treble. We want to make sure that there are no sudden peaks or dips in the curve that would indicate that certain frequencies are being emphasized or attenuated with respect to the rest of the spectrum. We'll follow the white paper recommendations and measure this at 80 dBA with monophonic correlated pink noise on both channels. 80 dBA is used as it's a typical listening level in the car, and usually the head unit doesn't use loudness compensation at this level. Let's make a measurement. I've already calibrated the level, so I know it's at 80 dBA, and we should play it for 30 seconds, but to speed up this demo, I'm just going to play it for 3 seconds. I'm still going to get a pretty accurate result, just maybe not warming up the speakers as much. First, it asks for the car model. I'll say Tesla, and we're measuring in the driver's seat, 1L, and we're ready to go. Okay, the overall level is 79.5 dB, quite close to 80, with a delay of 1.45 seconds, which SoundCheck has measured and compensated for. Everything's good. Let's hit save. What I've actually done here is a third octave analysis of each individual microphone 1 through 6, and you can see the difference due to location, reflections, and standing waves in the car. The black curve is the overall power average or spatial average of all 6 mics as specified in the AES white paper. The difference in the response of the individual microphones due to location, reflections, and standing waves in the car is clearly a little bumpy, especially above 200 Hz. But the spatial average response is fairly smooth, which correlates to how a human would perceive the sound in the car. You can see the microphone closest to a particular loudspeaker, for example, the speaker in the door, typically has a higher level than other microphones at some frequencies and lower at other frequencies. Also, I can bring up the memory list and protect this overall spatial average so that I can compare it to the uncorrelated pink noise measurement in the next measurement. So now we're ready to measure the frequency response using uncorrelated pink noise, which means that we will not be playing the identical pink noise into the left and right channel, but they actually will be randomized between the 2 channels. We expect some low frequency cancellation due to phase differences. So let's run the sequence and see what we get. Again, it's asking us for the model and the seat location. Hit OK. And there we go. So first of all, I'm going to save this, and you can see I still have the old curve where I was measuring the correlated pink noise in my memory list. So let's just bring them up separately on 2 different graphs. So we go here and click on here, and we can just drag them onto the screen. The orange line is the correlated spatial average, and the black line is the uncorrelated spatial average. We can see that uncorrelated pink noise has about 3 dB less output than the correlated pink noise below 100 Hz and very little above 1 kHz. Something else we can look at is the seat-to-seat spectral uniformity. Ideally, each passenger in the car experiences the same high-quality sound performance from the infotainment system. However, it's extremely difficult to independently equalize the loudspeaker playback system for each seat in the car. Trade-offs are made when the system is tuned, typically favoring the driver's seat. This results in the frequency response in the other seats being not as smooth or ideal. In this measurement, we repeated the first frequency response measurement with correlated pink noise in each of the car's 4 seats. And here are the results. You can see that the bass performance in the rear passenger seats, orange and green lines, is not as extended or smooth as the front passenger seats. To calculate the seat-to-seat spectral uniformity, we compare the individual seat response to the maximum and minimum responses to find the seat with the biggest difference. In this example, both the left and right rear passenger seats have over 10 dB difference from the front seats at some frequencies. The lower the number, the more uniform the frequency response is from seat to seat. Now let's look at distortion. THD indicates the overall nonlinear performance of the device. If the THD is outside the limits, it may indicate a poorly centered voice coil or mechanical defects. We also measure the total harmonic distortion at 80 dBA, this time using a step sign sweep stimulus with 12th octave steps. If we bring up the stimulus here, you can see that there's some averaging time, but we try to make it fairly quick so that the system's compressors don't kick in. We sweep from high to low because that generally achieves more consistent results than sweeping from low to high. This is because the compressors do not activate as quickly and the speakers ring for a shorter time than they would if hit with a high-level, low-frequency step at the beginning of the sweep. I'm going to hit Start, enter the model. Now you may have noticed it was very quiet towards the end of the sweep, and that's just because the car system cannot really output below 20 Hertz. As before, we power sum the spatial average of all 6 microphones to produce the THD power average curve, this black line here. This smooths out the standing waves and reflections picked up by the individual microphones. So that's not too bad. If we look at the power average, we're getting roughly 2.2% from 50 to 10 kilohertz. Next, we're going to look at intermodulation distortion. This is a good test for multi-way speaker systems with a crossover. If a small driver is trying to play back low and high frequencies simultaneously, it will struggle to play both frequencies and create intermodulation distortion. Before I jump into the measurement, let me just explain the stimulus. IM distortion measurements use a two-tone stimulus with a fixed tone at a low frequency and a sweeping tone. The fixed tone, F2, is set to 50 Hz, typically in the subwoofer frequency range. The precise value is not important, but it should be near the speaker's resonance and below the crossover frequency. The master tone, or sweeping tone, F1, sweeps high to low from 20 kHz down to 150 Hz for measurement stability. Typically, the sweeping tone stops at around 3 times the frequency of the fixed tone to avoid the respective tracking filters from overlapping and resulting in measurement errors. When I made this measurement, I first swept from 20 kHz to 200 Hz to ensure the auto delay was correctly set and to auto range the input gain for the best signal-to-noise ratio. Distortion harmonics can be as much as 60 dB below the fundamental and still be audible. This means it's important to maximize the dynamic range by setting the input gain so that the harmonics are above the noise floor of the measurement. Anyway, I've already done that, so we can jump straight into the measurement. There we go. This looks like a good measurement here. I'm going to save it. The graph shows the fundamental and total intermodulation distortion of the second and third order intermodulation products, power averaged from the 6 microphone array. And as you might expect, there's more intermodulation distortion at the lower frequencies, but you can see an increase around 700 Hz. That's probably a crossover frequency in this car. And if we take the spatial average of all 6 mics, we get 1.4% overall level of intermodulation distortion. So that would be an average, and we're getting a playback level of roughly 75 dB. I'm not exactly sure why we're not getting 80. Maybe there's some compression going on. Maximum SPL is one of the measurements outlined in the TC-AA proposal. It enables comparison of the maximum volume of the infotainment system. It's defined as the maximum sound pressure level that a car's infotainment system can reproduce inside the car's cabin with its windows, sunroof, and convertible top closed. The measurement combines all the components of the system: speakers, amplifiers, power supply, etc. There are many ways we can measure this, but to keep it simple, the TC-AA committee recommends 2 different measurements: overall max SPL and max SPL spectrum, regardless of distortion level. For this measurement, we set the car's volume control to maximum. We measure overall max SPL and SPL spectrum simultaneously using broadband 20 to 20 kHz minus 12 dB FS monophonic pink noise stimulus with a crest factor of 12 dB. The stimulus is played for 30 seconds to ensure that the level could be sustained continuously. I'm not going to show the actual measurement here as it's very straightforward, and I've made a couple of demos of this before. Instead, I want to show you something similar but more advanced. We'll just take a quick look at some results. Here you can see the results of the standard TC-AA Max SPL measurement. Like in other graphs, we see the individual microphone measurements and the average, the black line. The overall level of 103 dB C-weighted, regardless of distortion, is not too loud. It may be limited by design to prevent severe distortion at low frequencies from clipping the amplifier. What I'm going to show you instead of a straightforward Max SPL measurement is maximum SPL at the onset of audible distortion. Most audiophiles would agree that louder is only good as long as the output sounds good. So it's easy to argue that defining the maximum SPL should be based on the onset of audible distortion. We have several other loudspeaker standards based on measuring Max SPL this way. Since compressors and limiters have a time constant to allow for short-term transient peaks you often find in music, it's possible to measure the maximum SPL and distortion before they take effect. For example, you can measure relatively accurately without damaging the speaker at high test levels using a short tone burst. Although I think this is a more valuable measurement, it is a much more complex test sequence and takes longer to run the test. You need to repeatedly play the stimulus until you reach distortion levels across a range of frequencies, similar to how we measure Max SPL and other applications. The good news is it's not difficult if your software system allows good test flexibility and the process can be highly automated. Our test sequence plays the stimulus multiple times for each test frequency, increasing the level in 3 dB steps until the THD exceeds 3%. We then reduce the level by 3 dB and increase it in smaller increments of 0.5 dB to more precisely find the 3% THD threshold. The Max SPL is recorded at that frequency, and the test sequence continues to the next frequency. The entire process is completely automated via the test sequence, making this measurement fast with minimal intervention. Let's take a look. Let's run this measurement. This actually takes about 20 minutes to run in total, so we've edited it down for the seminar to skip the repetitive bits. So let's hit start and I'll walk you through it. As usual, we need to know the car model number. I'm going to start at 50 Hertz because the car really can't output much below 50 Hertz. So let's go with that. I'm just going to go up to 500 Hertz because it doesn't get too difficult once you get to the higher frequencies. So let's say OK. And then here's the percent distortion. Once it goes above whatever I enter, for example, 3%, it will enter the maximum sound pressure level at 3%. And then continue to the next frequency. This is just telling me what the maximum input level is. It's pretty much based on the Bluetooth full-scale deflection, so just below 0. And the level I want to start at. I could start probably a little higher, but just to be safe, I'll start at -12. So the first thing it does is an auto range, and it measures the delay, the time delay in the system. Now it's playing 50 Hertz. It's auto-ranging. In a moment, it's going to show the first result. It's pretty loud. All right, here we go. So we can see the 50 Hertz sine wave of the 6 microphones capturing it. And we can see that we're around 3.4% distortion. So now it's going to lower by 3 dB. And it's going to start going up again. Looks like some compression or compressors kicking in. You can see the signal starts to go down in level versus time. So now we're at 114 dB at 2.4%. A little higher. So now it's going in half dB steps to very precisely find the sound pressure level at exactly 3%. I'm just going to skip quickly through the next few measurements until we start graphing results. It just went up by half a dB, and the distortion is 2.9%. Sound pressure level is 114 dB, so it's around 3% at 115 to 114 dB. Now we're starting to graph the results. So we've got 3 points now. We got 50, 63, and 80 hertz. And you can see on the bottom graph is the input level, and on the top graph, we got maximum sound pressure levels, the blue curve, and the orange curve is the THD level for that sound pressure level. Again, I'll fast forward through the rest of the measurements at high speed until we get our end result. The entire test takes about 20 minutes, and it's quite repetitive. It just does the same at a bunch of different frequencies. And there you have it. The top graph shows the maximum SPL and corresponding THD. The lower graph shows the maximum stimulus level plotted when the THD reaches 3% with the head unit's volume control set to max. At some frequencies, especially higher frequencies, for example 400 and 500 Hertz, the maximum input level is reached before the system distortion reaches 3% THD. The stimulus level is typically limited by the lower frequencies where there is more distortion. Since it is debatable how audible THD is, it's also possible to use other criteria such as rub and buzz distortion, which is quite audible to find the max SPL limit. Now I'll just save the data to disk. I'll just say yes. Okay, so that concludes our system performance measurements. Now we're going to move on to impulsive distortion, which is more of a system integrity metric. Infotainment system sound quality is sometimes limited by vehicle integrity. For example, the speakers may cause door panels, loose wire harnesses, fasteners, etc. to vibrate. This results in audible buzz, squeak, and rattle, which degrades the listener experience. Before we perform system characterization measurements, it's a good idea to ensure the infotainment system is properly installed in the vehicle under test. We can do this with an impulsive distortion measurement. This test may also be used as an end-of-line check to verify vehicle integrity. There are several ways you can do this. The AES white paper recommends a crest factor measurement with a logarithmic sine sweep and a tracking high-pass filter 10 times greater than the stimulus frequency to evaluate impulsive distortion at 80 and 90 dBA. Crest factor is the ratio of peak level to RMS level. A sine wave has a crest factor of 3 dB. Pink noise has a crest factor of about 12 dB. Transients such as rattling wires, loose fasteners, and noise, for example background noise, typically have a crest factor greater than 8 dB. Generally speaking, crest factors over 3 dB may indicate buzz, squeak, or rattle. However, you have to be a bit careful as background noise, especially in a noisy factory, may cause similar crest factor results. You need to be very careful to minimize background noise and make sure that the result correlates with what you can hear. There are a couple of other techniques that I prefer to use in place of this as they offer advantages: perceptual rub and buzz and transient distortion versus time. Specifically, they are less sensitive to background noise and only highlight distortion sounds that are audible to humans. Perceptual rub and buzz measurements use masking curves to simulate the performance of the human ear to measure only audible distortion. This method is also more immune to background noise than crest factor. Transient distortion versus time measurement tracks individual events in the time domain to reveal any loose particles or rattling wires with greater precision than in the frequency domain, since it tracks individual events. Crest factor, which is a running average, will smooth out some of the transients by the very nature of its calculation. Okay, let's run some measurements. We'll enter the car model again and start the test. There's a couple of frequencies there where I could hear some buzzing or rattling sound. I'm not sure if you could hear it. Let's see if we can pick that up in the measurement. All right, so there's the recorded time waveform of all 6 mics. And on the second graph here, I'll just go ahead and hit save. We see perceptual rub and buzz, and indeed there's a bit of a peak at around 224 Hertz, and also at a higher frequency here, around 340 Hertz. Those are the little buzzing sounds that we heard during the sweep. Now, if we look at the bottom waveform graph, we can see if there's any transients. Those transients are typically things rattling around. Now, at low frequencies, we don't have a lot of output, so it's probably just background noise. I'd say it's really not an issue. As you can see at low frequencies, there's just not a whole lot of signal to noise ratio. So although this was a good demonstration of the tests, the car only had a tiny bit of rub and buzz and no transient artifacts, which is good because it's my car and buzzing speaker would really annoy me. When we remeasure it at 90 dBA, you can hear audible distortion. Let's just take a listen to the recorded response. Can you hear the distortion? Now this is quite obvious, and you can see it even shows up in the crest factor response. You can see the crest factor is above 8 dB between 200 and 300 Hertz. Now if we look at the EPRB curve, you can see a peak in the same point showing it correlates well. This is a little more sensitive though. On this one, we can also see a smaller, sharper bump at 600 Hertz, which is not perceptible in the crest factor measurement, although I could hear it during the sweep. This measurement technique is also considerably more reliable in a noisy environment. This third graph shows the time transients of the impulsive distortion measurement. You can see transient spikes from the measurement microphones number 4 and 5 around 11 to 12 seconds into the sweep. These are closer to the driver's side door, where some door panel rattling is occurring at low frequencies around 200 to 300 Hertz in the sine sweep. A neat trick with this measurement method is that you can actually listen to the recording without the fundamental. Let me just play that back now. And that really highlights the audible distortion. So that pretty much concludes our suite of measurements. There are, of course, many variations of these measurements, as well as other things you could measure with the same physical hardware setup. But that's all we have time for today. Let's just summarize what we've covered. Measuring vehicle infotainment systems is increasing in complexity. More and more speakers are being installed in cars at various locations, including the headrest and ceiling. There's more signal processing, for example, Dolby Atmos. Vibration exciters are even being added in the seats of some cars to extend bass response. This means that measurement methods must constantly evolve to keep up with these advancements. This will involve vibration, electrical, psychoacoustic measurements, as well as basic acoustic measurements, so that we can correlate measured data to human perception of sound inside a car. The equipment configuration used in the TC-AA measurements is also good for many other automotive audio measurements. This makes it easy to further develop and customize in-car audio tests for more extensive characterization. I've shown you some of these here. It's important to develop standardized measurements so we can compare performance of different vehicle audio systems. Calibrated measurements of frequency response, distortion, and maximum SPL is a good foundation for objectively analyzing the performance of the vehicle's infotainment system. Impulsive distortion measurements are an effective way to check the vehicle's build integrity before making car audio measurements. The TC-AA white paper is currently in the review period. We hope a lot of people will experiment with these measurements and provide feedback. This will drive updates to the proposal to ensure that the methods are practical for most manufacturers. Please do download the TCA white paper and make some measurements following its guidelines. This QR code here will take you directly to the AES webpage where you can get a copy. We hope these measurements will eventually lead to the development of an industry standard.